This lesson's about the force that an external magnetic field exerts on a current-carrying wire. Here are your objectives. Now, in the previous lesson, we looked at the force that an external magnetic field exerts on charged particles that are moving in that field. And a current-carrying wire can be thought of as just a bunch of charged particles moving in a field. So here, if we have positive charges in the wire moving to the right, so the conventional current is to the right, or equivalently, if we have negative charges moving to the left, then using the right-hand rule we saw in the previous lesson, we point our fingers in the direction that the positive charges are moving, here to the right. We fold our fingers in the direction that the external magnetic field is, here, that's into the page. That leaves the thumb of our right hand pointing upwards, and so we see that the magnetic force is going to be upwards on each of these positive charges. And so it stands to reason that if you have a current-carrying wire with a conventional current moving to the right, as is shown here, then similarly, this external field pointing into the page would generate an upwards force. So the right-hand rule that we've seen for positive charges moving in a external magnetic field applies to current-carrying wires as well, as long as we think of conventional current. So that's the direction. What about the magnitude? Well, if we take a look at our formula from the previous lesson, the magnitude of the magnetic force is equal to the charge times the charge's velocity times the magnitude of the magnetic field times the sine of the angle in between the velocity and the direction of the field. That's our formula from the previous lesson. We can now derive from that a formula for a force on a current-carrying wire. Let's imagine that we observe this system for a time delta t. So I'm going to actually multiply top and bottom here by delta t. So qv delta t over delta t. Again, I'm just multiplying top and bottom by delta t, and then I still have b sine theta. Well, what does v times delta t mean? Speed times time gives us distance. So if I'm observing this thing for a time delta t, and the particles are moving with speed v, they will move through this distance. In other words, they'll move through a length equal to v delta t. So this is just the length of wire that the particles move through. And q over delta t, charge per unit time, is our definition for current. So by multiplying top and bottom here by delta t and rearranging a bit, I've got a formula now in terms of current, the length of the wire that the particles move through, and then b sine theta. In other words, I ended up with I times L times b sine theta. And this is our new equation for the magnitude of the force on a current-carrying wire in an external magnetic field. For the direction, we just apply the right-hand rule like we did before. Instead of pointing our fingers in the direction of the particle's velocity, we just point our fingers in the direction of the current. So to summarize, the magnitude of the force on a current-carrying wire in an external magnetic field is equal to the current times the length of the wire that's in the field. So this is the length of the wire that's actually in the field. If the field ended right here and right here, then we'd be talking about this length, multiplied by b times sine theta. And here, theta, again, is the angle between the wire and the external magnetic field. In the picture shown here, it's 90 degrees because the wire is going left to right and the magnetic field's into the page. If I want to think about the direction, it's helpful to write this in our cross product notation that we saw in the previous lesson. So I times L is actually a vector that points in the direction of the current. Current's not a vector, it's a scalar, but L is the length of the wire pointing in the direction of the current, crossed with the magnetic field. Again, like we saw last time, we point our fingers in the direction of the current, or the length of the wire in the direction of the current. We fold them in the direction of the magnetic field, and then our thumb points in the direction of the force. Let's do a little bit more practice with a field oriented in a different direction. Let's make this the north pole of a magnet. This is the south pole of another magnet. And therefore, our magnetic field lines would be pointing from left to right here. And they would go like this. And let's say that this is a wire with a current traveling upwards. So conventional current is moving upwards. And remember that all of these right-hand rules that we're talking about refer to the direction of positive charges and therefore conventional current. So if we use our right-hand rule again here, we point our fingers in the direction of the conventional current, that's upwards. We have to orient our right hand so we can fold it in the direction of the magnetic field. That's therefore so that we can fold our fingers to the right here. When we do that, our thumb points into the page, and so the direction of the magnetic force is into the page. And we would indicate that by an X, like as if we were looking at the back of an arrow. So that's just another example. Just to extend that, if we were to make this into a loop of wire like this, so now on this side, the current is traveling downwards. Then we've just said that here on the right-hand side, the direction of the force is into the page. So this bit of wire pointing upwards would feel a force into the page like that. However, over here, if we point our fingers downwards in the direction of the current, fold them in the direction of the field, so to the right here, then our thumb ends up pointing out of the page. So this is the force over here, and this is the force over here. And so we can see that this loop of wire would actually tend to twist as this rightward part goes into the page and this leftward part comes out of the page. And that's actually the principle behind an electric motor. You put a loop of current carrying wire in an external magnetic field, do a little bit of clever engineering to allow it to keep spinning, and these forces will make this loop spin and anything attached to it, like a wheel, spin as well. So that's a look at the force that an external magnetic field exerts on a current carrying wire.